Hello, and welcome to this video about interference. We're going to talk in this video about constructive and destructive interference for light, what coherence means, demonstrating interference, and how to calculate the location of interference fringes. Remember that when waves interfere, energy is not lost, it is just redistributed. Here we have two waves that have identical wavelengths, and they are interfering when they cross each other's paths. And in this case, they're interfering constructively. Here's the resultant wave. Here is destructive interference because they are out of phase with one another. Remember the superposition principle and that the displacement at any instant when these waves interfere is going to equal the sum of the displacements of the component waves, which is why we get what we get for the resultant wave. For interference to be observed, the waves must have a constant phase difference. Here's destructive interference. These waves are out of phase. They are not coherent. We use the term coherence to describe two waves with identical wavelengths that maintain a constant phase relationship. These waves are coherent, so we have constructive interference when the waves are coherent or completely in phase. So you've all seen what interference looks like with mechanical waves. What about light? What does interference look like when light waves are interfering? Here are some examples of light waves interfering, and when light waves interfere, we see alternating light and dark fringes. Here are some examples of these alternating light and dark fringes. So why does this happen, these alternating bands of light and dark fringes? Well, let's look at this setup here, where we have a monochromatic light source. A monochromatic light simply means light from a single color or a single wavelength. And we have this monochromatic light source that we are passing through a single narrow slit and then through these two narrow slits here, a double slit. And these slits here serve as a pair of coherent light sources because the waves emerging from them come from the same source here. Any random change in the light emitted by the source will occur in the two separate beams at the same time. When the light from these two slits arrives at a point on this screen where constructive interference occurs, we see a bright fringe. Here you can see these are the places of constructive interference. Here as well. And we see a bright fringe. When light from the two slits combines destructively at a point on this screen, then a dark fringe will be seen at that location. Something to note is that this pattern is much more complex for light that has multiple wavelengths. If we use white light, we're going to see an indistinct kind of pattern because the colors interfere constructively at different positions. So it isn't exactly a light band, dark band pattern like we see with monochromatic light. Here's another way to look at what we have just seen. When we have destructive interference between these two waves, you can see that this wave and this wave are traveling not the same distance. This second wave is traveling half a wavelength farther. So for destructive interference, there is a difference of half a wavelength right here, and that is producing the dark band. For this constructive interference, you can see here that you have the difference in the length that the waves are traveling is going to be one entire wavelength. And so we get bright or constructive interference when we have whole wavelength, a difference of a whole wavelength between the path length that the two different waves are traveling. Now let's take a look at how we name the fringes. Before we go any further, there's a special way we name them so that we all understand what we're talking about. The very central bright spot is called the central bright maximum. And the fringes on either side of it that are bright are called first order maxima. And then the next one would be the second order maximum on both sides. Third order, fourth order maxima. When we talk about the dark fringes, we look at the two dark fringes on either side of that central bright maximum. They are called first order minima. Then we have second order minima, the next dark fringes, then third order, fourth order, and so forth and so on. Now let's look at how we can predict the location of these different interference fringes. We know that if we have these two slits right here, slit 1 and slit 2, D, lowercase d, is going to be the distance between these two narrow slits. And we can use a little bit of trigonometry to set this up. We can look at the path distance or path length here as a lowercase l for the path lengths of those two waves that are traveling through those slits. And we can find the change in the path length here. And when we set up our little trig problem, we can see that delta L, or the change in that path distance, the difference between the two, is going to be equal to D, which is the distance between the slits, times the sine of theta. And theta is going to be this angle right here. So this allows us to write a couple of equations. The first one is our equation for constructive interference. And when we have constructive interference, this equation is going to represent a variety of variables for us. D being the distance between the slits. Theta is right here, the angle that is formed when we take the difference between those path lengths. And we have wavelength here, and we also have M. What is M? M is the order number of fringe. M equals 0 when we're talking about the central bright fringe. It will be a +1 or a -1 depending on which side of the central bright fringe we're on, or plus or minus 2, etc., etc. But it will be a whole number because this is for constructive interference. You can see from this equation that the path difference, this is equal to delta L, or the difference in the path lengths between these two waves. D sine theta equals that. And that path difference between the two waves is going to be equal to some whole number multiple of the wavelength. Remember, we talked about constructive interference is when we have a whole number multiple times that wavelength. That gives us the constructive interference. Now that should be an easy jump to our equation for destructive interference. Destructive interference is going to be an odd number of half wavelengths. So we're going to get, in this case, M is our order number of fringe. It's going to be 0 plus or minus 1 plus or minus 2, but it's going to be M plus 1/2. So for destructive interference, we're always going to get an odd number of half wavelengths. It'll be either 1/2. If M is 0, we're going to get 1/2. Or if M is 1, we'll get 3 halves, 5 halves. Those will be the kinds of numbers. Now, M stands for the order number of fringe. But when M is 0, it's actually first order fringe. When M is 1, it's going to be our second order fringe, and so forth and so on. So M is, it's the order number of fringe, but it's not, it doesn't exactly correspond with the name of the fringe. So now, knowing what you know, you can pause the video and ask yourself these questions. If the path distance of two waves differ by 1 wavelength, are you going to see dark fringe or bright fringe? What if the path distances differ by half of a wavelength? If their paths differ by 1.5 wavelengths, what order number of fringe are you going to see? Pause the video and see if you can figure these out, and I'll give you the answers on the next frame. If the path distance of two waves differ by 1 wavelength, you're obviously going to see bright fringe. It's constructive interference. And if their path distances differ by half a wavelength, you'll see a dark fringe because it's destructive interference. What about this question? You're going to see the second order minimum. And why is this? If you think about our central bright maximum right here, the two dark bands on either side are our first order minima, and those would be represented by half a wavelength. The next odd numbered half wavelength would be 3/2 wavelength, or 1.5 wavelengths. That's going to be second order minima, and that's why if they differ by 1.5 wavelengths, we're going to see second order minima. Let's do an example together. Let's say we have a distance between two slits of 0.0050 millimeters, and we want to find the angles for the 0th, 1st, and 2nd order bright fringes for the interference produced with light that has a wavelength of 550 nanometers. I'm going to start writing the things I know. I know the distance between the slits, and I'm going to convert that into meters and into a more convenient form. I know my wavelength. I'm going to convert that into meters. I'm going to find my angle for when m equals 0, for when m equals 1, and for when m equals 2 for constructive interference. My equation for constructive interference is here, so I'm going to go ahead and solve this for my 0th order when m equals 0. When I plug my values in, I get theta equals 0 degrees when m equals 0. If I replace m with a 1 for first order, and I solve this equation with a 1 here instead of a 0, I get theta equals 6.3 degrees. That would be the angle for the first order bright fringe. And if I replace this number with a 2 for second order, and I solve this equation, I'm going to get theta equals 13 degrees for the second order bright fringe. Here are a couple of advanced ideas. Apply the ideas of constructive and destructive interference to sound waves and explain how a piano tuner uses a tuning fork to tune the piano. Or Thomas Young, he first demonstrated this double slit experiment in the 1800s. Who was Young? There's a typo there. And how did his demonstration change the way we think about light? What other ideas did Young introduce? Maybe you have some other questions or other ideas that you've come up with. I look forward to seeing what you come up with. We'll see you in class.